Hello, everyone. We are going to continue in section 3.1 with the mole concept. So I'm going to start with the learning objective relative to this part, and then we'll move ahead. Define the amount of define the amount unit mole and the related quantity Avogadro's number. Explain the relation between mass, moles, and number of atoms or molecules, and perform calculations deriving these quantities from one another. You should have already watched the first part of this section on formula mass. So we're going to skip past that and jump into the mole concept. The first paragraph here is just talking a little bit about why this is important. I want to move ahead to this second and focus here, just in terms of really defining what we mean when we say the word mole in a chemistry concept. Mole is what we call a counting number. It is a number that we use, a word we use to represent a number when we're counting things. Other words we use in this way are words like pair or dozen. So when we say pair, we mean 2. When we say dozen, we mean 12. The word gross means a dozen, so 144. There are other examples of words that when we use those words, we mean a very specific number. So the word mole is a word that we use in chemistry to refer to a specific number of atoms or molecules. We could potentially use the word mole to count other things, like eggs or pieces of paper. However, the number ends up being so big that it's really not useful for things other than essentially atoms and molecules. And we'll look at some examples of exactly how big that is a bit later in the discussion today. So then the number that we end up with that works is this number right here. 6.02 times 10 to the 23rd is the number that mole refers to. This is giving you several significant figures here. For the sake of this class, 6.022, so 4 significant figures, will always be fine. Much of the time, 6.02 will be fine. More important, though, I should say, than these numbers is this one. Okay, so make sure you're getting the 10 to the 23rd part right, because if you get that part wrong, you'll be off by a lot. So 6.022 times 10 to the 23rd is the number that we're talking about here. We use the word mole to refer to this number. We also use the word Avogadro's number. We also use the word Avogadro's number to refer to this number as well. Okay, so these three things mean the same thing. Avogadro's number, 6.022 times 10 to the 23rd, and mole. As we'll see later, we often relate mole to other things in other ways, and it will become a central conversion factor. So that's why we have kind of three things that mean essentially the same thing. So we'll often refer to, Avogadro's number when we want to be using this, and mole, we will maybe sometimes be using that to relate to other things. But they all essentially mean the same thing. So a little bit about this number. So it came about from some experiments on gases many years ago. So that's why it's named after a person because of the work that they did. It's also a number that we have refined over time as we have better experimental evidence. Now, you might wonder a little bit about that because we didn't change dozen to be, something else. I guess we have the baker's dozen, which is 13, based on dropping one, potentially. So we don't change other numbers, other words as we gain more information. But we do that in this case because it actually makes sense to do so. As we gain more knowledge, as we gain better instrumentation, we can go from something with 4 significant figures to what we have up here, which is, it looks like 9 significant figures. So we can gain more precision on this number. And you might wonder, well, why didn't we just stick with what we came up with? The technical definition of the mole, and I don't believe your book, okay, we talked about it right here. So let's go and talk about the technical definition of the mole, and then we'll come back to what we do with that. So we define the amount based on this particular isotope of carbon, carbon-12, has 12 AMU. So we define basically everything in terms of masses for elements that based on this being what it is. So carbon-12 weighs exactly 12 AMU. If we find out with greater precision that it's maybe a little bit different than that, then we redefine AMU so that that is true. And so that's kind of where we end up rearranging Avogadro's number to make that true. And when I say we end up rearranging, what I mean is over the course of several decades, as better instrumentation becomes available, some of these later digits become will change a little bit, so that is true. So the reason we do it in that way is because the mole concept becomes very useful not for counting atoms per se, but for dealing with macroscopic quantities of matter. And we're seeing a picture here showing some of those macroscopic quantities. We have an additional use of the mole concept linked back to the formula mass. And that is that if we have 1 mole of an element, the mass of that is the same as the formula mass, except the units are changing. So instead of AMUs, we end up with units of grams. So we talk about grams per mole, and we'll be using this throughout the rest of the semester. So the mass of 1 mole of an element in grams is equal to the formula mass in AMUs. We made the distinction in the first part of this section between formula mass and molecular mass. We can just, from here on out, use the term molar mass, okay? And molar mass is the mass in grams of 1 mole of whatever that is. So 1 mole typically of an element or of a compound. So here we're showing some examples. So if we look on the periodic table at these substances, and here we're showing to just 3 significant figures. So let's go back to our periodic table. We can see zinc 65.38 to 3 significant figures. We're calling that 65.4, and that's grams. Okay, so this is 1 mole of zinc. And then similarly for these other elements. Now, one thing you might notice is that, depending on the element, we might have a bigger mass or a smaller mass, and that's essentially based on the way the mass works for the atomic masses of the elements. So something that's larger. From here, I think the largest one we have might have been maybe the 10. So for 10, we have SN is 10. We have a larger mass compared to carbon. Is about twice the mass. I'm sorry, not twice. It's about 10 times the mass of carbon. So this thing is about 10 times as big as this thing. And that's simply based on within those atoms you have more protons and neutrons here than you do here. Okay, so we're linking these things we can observe in the lab back to what the atoms are basically made of. But the molar mass concept is a very important concept that will continue not just through the rest of this module, but through the rest of the semester. Here we're showing in a table kind of a summary of some of these ideas. So we have an element, we have the average atomic mass of that element in AMU. Okay, so if we have one element, on average, this would be its mass. Of course, with the isotopes, you're going to have different specific atoms. But more generally, for the molar mass, if we have a sample we can put on a balance and find the mass of, if we get 12.01 grams, that means we have 1 mole of that element. And then we have atoms per mole. So in every mole, we have Avogadro's number, 6.022 times 10 to the 23rd atoms will be present. So you'll notice for each of these different elements, we have a different molar mass. However, the atoms per mole remains the same. And that's because the mole concept is defined as being this number. The reason this concept is going to be so important is that the mole concept will be used to link between different ways of measuring things. So we might talk about, well, how many atoms do we have? The mole concept would be a conversion factor that gets to that. We might want to know how many grams we have. The mole concept would be a conversion factor that gets to that as well. As we go forward, as we introduce new concepts, especially in Module 4, we'll be introducing several new concepts that each one, as we introduce it, we're linking the mole concept to some other idea. So the mole concept will be the central factor that we'll be using in conversion factors. There'll be additional ones throughout the rest of Module 3 as well. I want to talk a little bit about this example. So the example they're talking about here is if you have a drop of water and you take all of the water molecules in that drop. Is that what they're saying? Yeah, water molecules in that drop. And you distributed those water molecules equally throughout everybody in the world. Everyone would have 100 billion molecules. Now that's hopefully you can kind of, from that, get a sense of appreciation for just how big the mole number is. But maybe not, because 100 billion is also a number bigger than we can understand, as well as the number of people on the earth is a number I think is, once we get into billions, it gets very difficult to understand that. I'm going to share a few other examples to help you appreciate this. One of the labs that we do in one of our other chemistry courses is counting grains of sand, and from counting the grains of sand, figuring out how big is the mole. So if you had a mole of sand, how much would that be? What students typically find is they're not counting to a mole. Nobody would ever be able to do that. In fact, what they find is that based on their calculations, all of the beaches of California have about 1% of a mole of grains of sand. And we count beach there as going out to the continental shelf and going down fairly deep. So that's one way of looking at it. Another one I share sometimes is if we were to cover the earth with cover the oceans with ping pong balls, would we have? How many moles would that be? So if you cover all of the oceans of the Earth with ping pong balls, you would have to have enough Earths to stack from the sun out to Neptune about 4.5 times. So Earth to Neptune, and do that 4 more times, and then get partially out there again to get to a mole. And each of those Earths has the oceans covered with ping pong balls. Another one I sometimes share is if you had a mole of dollars, how long would it take to spend your money? And you would have to spend $1 billion a second from the time you were born. And then if you lived to about 65, and you had to spend $1 billion every second, even when you're asleep. If you could somehow figure out how to do that, you would only go through about 1% of the money, if that were the case. So I'm sharing these examples not because I expect you to memorize them, but just so that you appreciate when we talk about this number with 6.02 times 10 to the 23rd, how absurdly large a number like that is. Okay, where I want to leave this with, there are several examples here using some conversion factors. The mole concept is very central, very, very central to the rest of both this chapter and the rest of the semester. Probably this is the most important section, other than the initial conversion factor, which the reason this one is important is because it continues on those same concepts. Most important section of the semester. What I would encourage you to do is look at each of these examples. Try to solve it before you look at the answer. So there's 1, 2, 3, 4, 5, 6. There's 6 examples here. I would do the first 6. This one, maybe the neurotransmitters. I guess this is not an example problem, not as important. So I would do each of those where you, again, read through the question, don't look at the answer, try to do it, and then try to do the problem. Additionally, there will be several questions on the worksheets related to this concept. I'm also going to share in a separate video, probably a video that I've used for another course, solving a question on solving basically a mole question. So I would recommend watching that as well. If you're, I would try these examples first. If you can get them, then you're probably fine. If you feel like you need to watch somebody go through doing the problem, then watch one of those videos. I wanted to have that as a separate video, in part because we want to, use our textbook for this course, and then we'll have a separate videos for additional information. And then also, if it's more helpful to you to just skip to the videos where I'm going through things, you can more easily do that. So again, please, before you move forward to the next section, make sure you have mastered the mole concept, either by doing these examples, doing the worksheet problems, watching the other video that will be available that's going through a worksheet problem, or finding another relevant resource out there. But make sure you feel comfortable solving something similar to the examples here or what's on the worksheets prior to moving on to the next section.